had studied about kernel machines. We had started to study a support vector machine. So usually the idea is to separate two classes using a hyperplane. We had considered some examples in the previous class. So here we are having two classes, green class and red class. So this hyperplane separates this green class and red class. So equation of this separating line is 5x plus 3y minus 535 equal to 0. So we can draw several separating lines between these two classes, these two positive instance and negative instance. So there will be some gap between these two classes. So this is maximal margin separating line. That is the best separating line is the one with the maximum margin. So we had drawn some perpendicular distance from each and every point to the hyperplane. So shortest perpendicular distance is known as margin. Our aim is to find out the maximal margin separating line. So we have to find out the shortest perpendicular distance of the separating line. The separating line with the maximum margin is called maximum margin line or optimal separating line. So this line is also called, so this hyperplane is known as support vector machine. So here we got another line, equation 7x plus 6y minus 595. So this is the margin. So margin means here we are having a separating line, hyperplane, and we have to draw two parallel lines to parallel to hyperplane. So this line must pass through these points. So and these points are known as support vectors. So we have two classes, target equal to yes and target equal to no. So here we are having two planes, alpha 0 plus alpha 1, x1 plus alpha 2, x2 greater than 0, and this one is less than 0. So consider the perpendicular distance from the training instances to the hyperplane edge and consider smallest such perpendicular distance. So double of the smallest size is known as margin. So our aim is to find out the hyperplane for which the margin is the largest. That is maximum margin hyperplane, or it is known as optimal separating hyperplane. This maximum margin hyperplane is called support vector machine. The data points that lie closest to the maximal margin hyperplane are called support vectors. So these are the margin. So we are having two class linearly separable data set of n points of the form. So we have two class. So we have 2 points, x1, y1, x2, y2, etc. So since we have two class, we are having y's are either plus 1 or minus 1. So we are having alphas. So our first aim is to find alpha. Alpha equal to, so here we are having n points. So we have alpha 1, alpha 2, etc. alpha n. So this must maximize this phi of alpha. Phi of alpha, no need to study the derivation of these algorithm. You can just by heart this one. So we are studying the algorithm of SVM. So we are going to write the equation for this hyperplane. Okay, this one is sigma I equal to 1 to n alpha I minus 1 by 2 sigma I equal to 1 j equal to 1 to n alpha I alpha j y I yj x I xj subject to sigma I equal to 1 to n alpha I yi equal to 0 alpha I greater than 0 for all I equal to 1 to etc. n. And the next step is, so we have to find the weight and bias using these two equations. So for each non-zero alpha indicates that the corresponding xi is a support vector. So f of x equal to sigma alpha I, that is weight into alpha I wi xi weight transpose x. Fx actually fx equal to wt. Fx equal to wt x plus b. So you can substitute wt, that is this one. So we already know the value of b, this one. So notice that it relies on an inner product of the test point. So this x is the test point and the support vector xi. So also keep in mind for solving the convolution problem involved in the computing the inner product. So this one is the inner product xi txj between all training points. So next one is soft margin hyperplane. Actually in the previous class we had considered a two-class problem. And also it is to be noted that the data are linearly separable. Data are linearly separable means we can separate those data using a single line. In real life problems, actually the two-class problems are not linearly separable. So if the data are not linearly separable means it will be scattered. We cannot separate those data using a single line. So in those cases, we will introduce additional variable psi, eta called slack variables which store the deviation from the margin. So there are two types of deviation: an instance which may lie on the wrong side of the hyperplane and may be misclassified. So if an instance lie on the wrong side of the hyperplane, it is considered as misclassified. Or it may be on the right side but may lie in the margin. So yeah, and it is not sufficiently away from the hyperplane. So if eta equal to 0, then xi is classified correctly and there is no problem with xi. If eta I is between 0 and 1, then xi is correctly classified, but it is in the margin. If eta I greater than 1, then xi is misclassified. The sum sigma I equal to 1 to n, eta I is defined as soft error, and this is added as a penalty to the function to be maximized. So in order to avoid this, we introduce another factor c to avoid this soft error. So we can reformulate the SVM problem in the previous slide as follows. So this is why we introduce this eta term, soft margin hyperplane, because the algorithm for finding the SVM classifier will give a solution only if the given data are linearly separable. But in real life, two-class problems are rarely linearly separable. That's why we had introduced soft margin, introduced additional variable called the slack variable which store deviation from the margins. So we reformulate the problems like this. Given a two-class linearly separable data set of n points of the form x1, y1, x2, y2, etc., xn, yn, where yi's are either plus 1 or 1, find the vectors w and eta and a number b which minimize 1 by 2 mod w square plus c into c is a soft error, sigma I equal to 1 to n eta. So we will get like this. So this is eta greater than 1. This region is eta greater than 1. This one is eta less than 1. So this is the margin. So these are the support vectors. The points lie on this margin, then eta equal to 0. That is correctly classified. These points are correctly classified. So actually this red one. Here we are supposed to get a blue point here, but here we got a red point. So it will be misclassified. So it will be subject to yiw into, so this is inner product, w into xi minus b greater than or equal to 1 minus eta I for I equal to 1 to n, and eta I is greater than or equal to 0 for I equal to 1 to n. So some remarks. There are algorithms for solving the reformulated SVM problem given above. The details of this algorithm are not discussed here, and the hyperplane equations are given by these two equations with the values w and b obtained as solution of the reformulated problem are called soft margin hyperplane for the SVM problem. So we are having, this one is the soft margin. It is here we are having eta I. So this one is a hard margin SVM. Notice. Actually, this one is, we will get a small margin here in the case of hard margin. In this case of soft margin, we have a slack variable and we will get a large margin here. We will get a misclassified point here. That is the case of soft margin. In a hard margin, we will get all the points are correctly classified. Soft margin always have a solution. Soft margin is more robust to outliers. That is, there will be smoother surfaces in the case of soft margin. Hard margin do not require to guess the cost parameter. So kernel functions. So in this case, actually the data is not linear. We cannot use a straight line to separate the blue points and red points. Here we are using a kernel like this. So this is our hyperplane. This black line. Black line separates the red dots and blue dots. So we have kernel function. In machine learning, a kernel is usually used to refer to the kernel trick, a method of using a linear classifier to solve a non-linear problem. Kernel function is what is applied on each data instance to map the original nonlinear observation into a higher dimensional space in which they become separable. So definition. So actually this one is a kernel function. We are using this black line, curve, black curve, not line, curve. So here actually we can map the original nonlinear observation into the higher dimension. So if we are mapping, then it will become linear. That is kernel function. Kernel function means we are mapping the original nonlinear into higher dimension. If we are mapping like that, then we will get a linearly separable form. So this is the definition. In the context of SVM, a kernel function is a function of the form k of x, y, where x and y are n-dimensional vectors which have a special property. These functions are used to obtain SVMs like classifier for two class of data sets which are not linearly separable. Definition. Let x and y be arbitrary vectors in the n-dimensional vector space R raised to n, where let phi be the mapping from Rn to some vector space. A function kxy is called a kernel function if there is a function phi such that kxy equal to phi x dot phi y. So this question is also important. You are asked to write the important kernel functions. Homogeneous polynomial kernel is defined like this, where d is the positive number. Non-homogeneous polynomial kernel is defined like this. So there we have RBF, radial basis function kernel. So this is called a Gaussian radial function, and another kernel function is Laplacian kernel function, and next one is hyperbolic tangent kernel function. This is otherwise known as sigmoid kernel function. You have to by heart all these equations. Actually, this one is a very important question. Okay, how to map this kernel space? So we are having, so this is our original space. Actually, we are going to map a phi function. We have to find out this phi function. This one is mapped to this higher dimension. So this one is, actually this is the original space. So we are mapping to the higher dimension. So here we are using 3 dimension. So we got a point like this. In this case, we can separate the problems. Look at this, it is very easy. So these 2 points, these 2 triangles are mapped to a this higher dimension. So we can separate it. Again, this shape is mapped to this one. Like that, we can continue. We show that this is a kernel function. So this is the example. If you want to study this, you can do it. It is very simple. So next one is kernel method, or otherwise it is known as kernel trick. So this is also an important question. So we have 3 steps. First of all, you have to choose an appropriate kernel function. In the previous slide, we had studied the kernel functions. Then formulate and solve the optimization problem obtained by replacing each inner product xy by kxy in the SVM optimization problem. In the formulation of the classifier function for the SVM problem using the inner product of unclassified data Z and input vector x, replace each inner product xx, zx with kzx to obtain the new classifier function. First find the kernel function, then formulate the optimization problem. We had actually this inner product, replace this inner product with this kernel function. Then again, here we have inner product and replace this inner product zx by kzx. So in the previous slide, we had find the alpha, then w and b. So this is the algorithm for kernel trick. Find the alpha which maximizes this equation subject to this one. So this is very important. Finally, SVM classifier is given by. Okay, this is the algorithm. First find alpha, then compute w using this equation, compute b, then SVM classifier is given by f is equal to this one. Function equal to w t x plus b. So this x is replaced by kwx. kwz. So then next one is actually the original SVM is used to separate 2 classes. Suppose we are having 3 classes. How will you separate this one using SVM? So this is multi-class SVM. So we are having 3 classes. This is class 1, class 2 and class 3. So 3 class problem. So first of all, class 1. This is considered as 1 class and these 2 classes are considered as second class. So this is rest, class 1 versus rest. In next case, class 2 is considered, the others are considered rest. Here, class 3 is considered, others are considered rest. So that is, this method is known as 1 against all or OAA method. This one is 1 against 1. First we will consider class 1 versus class 2, then class 2 versus class 3, then class 3 versus class 1. SVM applications. SVM has been used successfully in many real-world problems like test categorization, image classification, and in bioinformatics problems like protein classification, cancer classification, etc., and in handwritten character recognition. So what are the weaknesses of SVM? It is actually sensitive to noise. A relatively small number of mislabeled examples can dramatically decrease the performance. That is, it is sensitive to noise. So actually it considers 2 classes. So how do we classify multi-class? So with multiple ART, M, learn, M SVMs, that is SVM 1 learn output 1 versus output not equal to 1, output 2 versus output not equal to 2, output M versus output not equal to M. To predict the output for a new input, just predict with each SVM and find out which one puts the prediction the furthest into the positive region. Classification with SVM. So given a point x1, x2, we can score its projection into the hyperplane. So in the previous slides, we know that if it is a non-linear problem, we will project it into the hyperplane. So here, these points, we are projecting these points into this hyperplane. And in 2 dimensions, score is calculated like this. That is w1 x1 plus w2 x2. These 2's are subscript. Here also, this 1 is subscript, 2 is subscript. So computing score will be like this, wx plus b. Here we have to set a threshold value t. If the score is greater than t, then it is yes. If the score is less than minus t, then the score is no. That is, we have 2 classes, yes or no. If this is not the case, we don't know the situation. So actually here we are having a misclassified problem, misclassified point. So then comparison with a neural network. In neural network, high hidden layers map to lower dimension spaces. In SVM, kernel maps to a very high dimension. In neural network, search space has multiple local minima. In SVM, search space has a unique minimum. In neural network, training is expensive. In SVM, training is extremely efficient. In neural network, classification is extremely efficient. In SVM, classification is extremely efficient. It requires number of hidden units and layers. Here we need cost and kernels. Very good accuracy in both cases. So this SVM is extremely robust. Actually, this question is also